Hi, I'm Alistair, and in this video I'd like to demonstrate how you can take a 1970s rotary dial telephone, such as this one, and turn it into an escape room prop using an Arduino and a DF Player MP3 module. Now, if you look around the internet, you'll be able to find various projects from people who have used these components together already. I myself did a tutorial about 3 years ago that was quite similar. And you can even find places that are selling ready-made props based on this hardware. But I think what I'm about to show you has the most complete feature set of any of the telephone props I've seen, and you can build it yourself for around £15. Okay, so what can it do? Well, first of all, you can trigger incoming telephone calls to the phone. So if I press this button, it will cause the bells in the phone to ring. Those are the real bells ringing. And the phone will continue ringing until either I hang up or the players pick up the handset to answer the phone. When they do so, they'll hear a recorded message.
Hello, your call cannot be taken at the moment, so please leave your message after the tone.
And that audio file that's playing there is saved on an SD card, which is capable of saving thousands of different pre-recorded messages, which I could trigger with different buttons, or perhaps they could be triggered by control software such as Node-RED. So to deliver clues to the players, for example, I could select which clue I wanted to send, cause the phone to ring, and when players answered it, they would hear the correct message. And you can also use it to simulate outgoing phone calls. So if players lift the handset, first of all they get a dialing tone, and then if they use the dial mechanism to call any number that has been defined in the code, you can associate different behaviours with different numbers. So for example, if I call this number, I get an engaged tone for now. And in fact, I can't do anything now until I replace the handset and dial again, just as you would with a real phone. But you can change the behaviour of that number mid-game if you wanted to. So perhaps the engage line stops being busy later on and players can dial it. Or if I dial a different number, for example, I initially get a ringing on the other end while I wait for the other person to answer.
Can you hear me now?
And then I get a different audio file. Again, these are saved on the SD card here, so you can have thousands of different audio files which you could use either for giving codes or to in some way develop the story or to give clues, things like that. Telephone numbers don't have to be the same length either. I was using two 5-digit codes there, but for example, let's say I wanted to dial 911, so that's just a 3-digit number. If I just dial 991, it will connect immediately with another different message. So it's really very flexible in terms of allowing the different phone numbers that you want to associate with different actions. I've just been using examples here that play audio messages because it is a telephone prop, but if you wanted to, you could trigger other hardware effects at the same time. Perhaps you want the players to dial a pizza delivery number, and when they do that, a pizza box gets shoved under the door that has some additional physical prop elements in it as well. There's really lots of things you can do with this. Now, when I made my last telephone prop project, I made a deliberate decision not to modify the handset in any way. And that was really for two reasons. Firstly, I think the design of these telephones is such a beautiful, iconic aesthetic, and I didn't really want to risk damaging that in any way. And secondly, I genuinely thought it would be easier if, rather than exposing the internal workings of the phone at all, I simply took an Arduino and wired it to the cable that you'd normally plug into the phone socket in the wall. It turns out I was wrong. The thing is, the workings inside the telephone itself are actually pretty straightforward. There's a mechanical switch that detects when the handset has been lifted. There's two more mechanical switches inside the dial mechanism. One of them detects when you start dialing, and another one opens and closes for each digit as it returns back to the resting position. Then there's a solenoid at the bottom, which when you activate that causes a clapper to move backwards and forwards. That's what rings the bells. And then you've got the earpiece and the microphone that have audio signals. Now, none of those components in themselves are actually that complicated, and it'd be pretty straightforward for an Arduino to be able to control them. It turns out the complicated and the clever bit is the way that all the functionality is combined into a very limited number of wires that go to the public telephone exchange. And it's also the bit that differs between different countries. So here in the UK, I've got a 4-wire connector here that would go into my phone socket. Some other countries have 3 wires or 2 wires. And the reason is because lots of those functions actually share the same signal. So for example, and you may remember this if you used to use these phones, the hook switch at the top here is the same as the dial switch that counts the numbers when they're returning. That's why you used to be able to dial phone numbers by just tapping the switch at the top a certain number of times. Likewise, the audio signals are carried on the same wire as the power signal to the phone. And the signal that controls the bells ringing backwards and forwards, well, that's actually an AC voltage, and it's quite a high AC voltage. It's somewhere between 50 and 60 volts. Alternating current causes that to swing backwards and forwards, which is not the kind of voltage you normally want to be using in an escape room where we like to keep things low voltage and DC, so 5 or 12 volts DC. So for this project, I made the decision to instead wire directly to each of those individual components. That's going to give me the most amount of control over exactly how they behave, and it's also going to mean that this project will hopefully work wherever you are in the world, what sort of handset you've got. And in the next section I'm actually going to show you how to identify how you are going to use all those components and how to wire them to your Arduino. So whichever handset you've got, if you follow these steps, hopefully you'll be able to get the equivalent behaviour. So this is my GPO746 handset, which were incredibly popular in the UK in the 1970s. And they have a single screw at the back here that's holding the handset together. So if I just unscrew that and then take the handset off, hopefully this will just lift up and you can see the inside. So what's lovely about these old handsets is that there is plenty of room to actually see what's going on inside them. We've got the mechanics at the front, we've also got these various wires and contact points here. So we'll start off by looking at the handset itself, and if I unscrew, so this is the speaker end of the handset. If I just pull that out, you'll be able to see we've got a pair of cables there. We've got a red and a green wire going to the earpiece, and on the microphone side of the handset, just put that to one side. If I lift that out, you'll see the microphone also has a pair of wires, a blue and white. And those 4 wires go down this curly cable here into the base unit. If I just pull that to one side for a moment, here we go. So we can see those are the 4 coloured wires that are entering the base set from the handset. And for the speaker, we want the red and the green wires that are attached here. So I'm just going to unscrew all of these. And what I say is sort of, I love this old handset because these are screw terminals. This is a totally reversible kind of procedure I'm doing at the moment. You know, if I want to put this phone back together, I can just screw these wires back in, and that's not a problem at all. So here we go. These are the wires that are required for the audio side of things. Let's set that to one side, and we'll look at what we've got left. So now let's look at the dial mechanism. So this is held on the front by a single screw that's here. So if I just loosen that, hopefully this will just pull away neatly. There we go. And this has actually got 5 wires going to it. Now we don't need to use all 5 of those, but we do need to identify what they do. And to do that, I'm going to try and show you up close the mechanics of how the dial mechanism works. This might be a bit tricky. Here goes. So the parts to notice are this switch here, which you can see hopefully is open at the moment. There's a little air gap between that silver switch and that gold switch. And this switch, which is currently closed. Now as I start to dial, watch what happens. The switch on the left closes. I'm dialing a number on the reverse side here. And then in a moment I'm going to let go, and watch what happens. The switch on the right will pulse up and down. And then the switch on the left, when the dialing's finished, will open again. Let me do that one more time. So I'm starting to dial. When I start to dial, the switch on the left closes. And then when I release the dial, which I'm going to do now, the switch on the right taps the number of times related to the digit, and finally when the dialing is ended, the switch on the left opens again. So now that we've seen the mechanical, almost clockwork action of the dial mechanism, what we need to do is to work out which of these screw terminals at the bottom we need to wire our Arduino into in order to be able to tell when these contacts are open or closed. So again, I'll do this for my particular handset. Yours might differ slightly, but hopefully you'll be able to follow exactly the same process, whatever handset you're using. So first of all, on this side, we had the dial pin. Now, this contact here was open by default, and then it closed against this contact here when we started to dial a number. Now, on my handset, that is connected to this screw terminal here, and it was originally wired into an orange coloured wire, so I'm going to colour it orange just in case that helps you to identify it if you're using the same handset as me. And then on the right hand side here we had the number pin. Now the number pin was the one that pulsed once for each digit in the phone number being dialed when the mechanism was released. This is a little bit harder to track this block here, but again on my particular handset that goes to this terminal down here, and it was originally wired to a brown wire in the wire harness, so I'll colour that brown. Now when the number was dialed, what that would do is that would flick against this contact here. Now what's interesting is that we can actually trace this copper coloured contact all the way through here and all the way out this side, and this is actually the same continuous piece here that is connected to this contact here, and this was originally connected with a pink wire. So just using these three connections here, we can tell when the number is started to be dialed, because that's when orange and pink make a contact here, and when the mechanism returns to the rest point, this is broken again. And on this side, when the dial is released and it goes back to zero, the brown and pink wires form and release a connection each time, so a pulse, which is why it's called pulse dialing, for each digit that is dialed. So those are the three connections that we need. Okay, so let's set that to the side, and now let's look at the hook switch up here. So this is the switch that detects when the handset has been replaced. Now this is actually a little switch on the side here, so what we need to do is find out which of those contact points that switch is connected to. And I'll do that using this multimeter. So if I take the probes here and touch them on two contact points, it's going to give me whether those points are connected. So these 2 points here are connected with a resistance between them that varies when I press the switch down. So 1, that means an infinite resistance. In other words, those switches are not connected, whereas a value of something like 7 shows that they are connected. So this point here is reading 1 whether the switch is up or down, so that is not connected. But this switch here, T19, you can see that the value changes as I press and release the switch. So that centre pin there and T19, that's what's connected to the hook switch. Okay, now let's go on and look at the ringer bells at this end here. Now these are powered by a little metal arm here that gets pushed to the left and right when these solenoid coils behind them are energised. If I just get these wires out of the way, these are the wires that are going to the dial mechanism, so we don't need them anymore. Let's just get rid of those. And you'll see what I've got left once I've done that is these two blue wires here. That's what's going to the solenoids. Now remember I mentioned that to ring the bell normally is an AC current that alternates direction. Now I haven't got that to hand, but I've got a DC 9-volt battery, and if I just wire it one way round to these two pins, watch what happens to that switch at the bottom. It moves to the side and it rings. Now if I swap them over, the arm moves to the other side, and I can keep on repeating this, reversing the polarity and making the bells ring. That's a rather lovely tone, isn't it? So the two switches there going to the blue wires, that's how we're going to make the phone bell ring, by reversing the current direction between those two wires. So we've got our speaker wires, the red and green. We've got the wires that go to the dial mechanism as well, that will detect when we've started making a phone call, and also the digit that we dialed. That was these wires here. We've also got the hook switch that detected when that was closed between these two contacts here. And finally we've got the two wires going to ring the bells, and that's it. And here's how I've got those four components of the telephone wired to my Arduino. Now, this diagram is fairly garish and a bit technicolor. The reason for that is because as much as possible I've tried to keep the color coding for the wires that I found inside my handset. Now, I'm not sure that's necessarily a convention, so your handset may well have different coloured wires, but just for the purposes of being consistent within this video, if nothing else, I thought that would be easier to follow if I kept to the same wiring convention that I've experienced, at least anyway. So we'll start at the bottom with the hook switch. So this, like I say, is a very simple mechanical switch that just has two connections. We've got the white wire here, and that is going to A0 on the Arduino. Now, there's no particular reason why this has to be an analog input pin. It could just as easily be any of the GPIO pins up here as well. I'm just using this pin because it happened to be on the correct side of the board to reach the component. There's nothing special about that at all. And then the other side of the switch here, we've got this black wire, and that is coming up here and joining with these two other wires here and going to ground. So this is a little bit complicated. So remember the hook switch, this is a very simple switch that either makes or breaks a connection between these two wires here. Now if we activate the pull-up resistor on the A0 pin that's coming in here, this means that when this switch is open, A0 is going to read high, and when it's closed, these two will become connected and A0 will read low because it's connected to ground. Now likewise, remember that we had a central pin in the dial switch, and that was either connected to the brown or the orange pin to let us know when dialing had started and also which digit was being dialed. So again, this is a ground wire that we're going to use to detect when either the brown or the orange have been pulled down. And in the earpiece that we've got coming up here as well, so we've got a ground wire and also a signal wire that's carrying the audio signal. Now this is sort of strikes me as odd here, seeing this red wire seeing a black wire, because normally I would use red to indicate a positive voltage. But the convention in telephone wire cabling is, so you've got the idea of an old style telephone socket would have a tip and a ring connected to it, like a kind of a headphone jack. And the tip is the green wire, and that's normally positive. The ring is the red wire, and so that is negative relative to the signal. So in this case it looks strange to me because we've got a red wire, which I would normally think of as a positive voltage, joining black, which I would normally think of as ground. But actually this red, this pink and this black wire here are all wired to a common ground here, and we're going to be able to use that to tell when the switches that are attached to A0, A1 and A2 are closed or open. So that green wire I mentioned, so that's the signal line for the earpiece speaker up here, and that is coming off our DF player mini module. So I've actually got it connected up here. This is to the left channel. Obviously a speaker in a telephone is only a mono audio line, so we don't need to connect both the left and the right channel. I've just connected to the left channel here. And we've also got, this is also connected to ground, to plus 5 volts. And then the white and the pink line here, well, these are used to carry the transmit signal from the Arduino to the DF player. That's what's going to use it to tell, to play a particular sound file, for example. And we've also got to transmit back from the DF player into the Arduino. and that's going to be used to send status messages back from the DF player to let the Arduino know what's going on. Now the issue here is that the signals on these lines are 3.3 volts, whereas the Arduino Nano I'm using uses 5 volt logic. So on the transmit signal here, I'm sending out from digital pin 4 of the Arduino. This is at 5 volts. By the time it arrives at the receive pin on the DF player, I want it to only be 3.3 volts. So to do that, I've got this pair of resistors here. So this is what's called a voltage divider or a potential divider circuit, because the voltage in a circuit, when you have a set of resistors in series like this, the voltage is dropped over them in proportion to their resistance. So this one is a 1K resistor, this is a 2K resistor. So a third of the voltage is lost across this resistor here, and 2/3 of the voltage is lost over this resistor. Now if we connect the point halfway between those two to the receive pin here, we had 5 volts going in, we lose 1/3 of that voltage, and that gives us exactly 3.3 volts, which is what we want to supply here. So this is called a voltage divider or a potential divider circuit sometimes as well. We've got our D4 output pin. This is going to be writing a 5 volt signal from the Arduino. We're going to connect first across a 1 kilo ohm resistor. Then at that point here, we're going to take the output to the receive pin. And then we're going to go across a 2 kilo ohm resistor here. So this is the greater voltage drop over this side. And this is wired to ground. Now, the pink wire here, this is transmitting from the DF player at 3.3 volts to the Arduino. Now, even though the Arduino expects to run at 5 volt logic, in practice those signals don't need to be exactly 0 for low and exactly 5 for high. There is kind of a range of values that will be interpreted as either low or high. And as it happens, 3.3 arriving here will be treated as a high signal, just as 5 was. So we don't need to do anything to step up the voltage of the return signal. We can leave it exactly as it was at 3.3 volts. That's fine. It's only the sending signal we need to step down, just to make sure that we don't supply voltage that's too high for the DF player to process. So we've got power, ground, input and output from the Arduino, and this output signal here is going to the signal line of our speaker. Then at the top we have our solenoids, which are ringing the bell. And remember, those are those 2 blue wires there. Now, to get this to ring the left and then the right bell, what we need to do is to be able to reverse the polarity of the current that's flowing between these solenoids. We want to send initially a positive on this line and a ground on this line, and then we want to send it the other way by sending a positive on this line and a ground on this line. Now we can't very easily do that directly from a pin that we write high or low to, so instead I'm using a motor driver here. So this is what's described as a mini motor shield. You can get slightly different style motor shields as well, but they actually work basically the same way. The main chip is something called an L293 chip, and we can control it using 2 input pins that go with the Arduino here. So they are connected to pins 2 and 3, and then we have a ground line and a 5 volt line. So all this side here is just about controlling the chip here and telling it how to write to these 2 outputs. So these are the 2 blue lines that are going to the bells, and depending on whether we write a high or a low signal to these 2 input wires here, if we write a high and a low this way round, the current will flow in one direction, or if we write a low and then a high, the current will flow in the other direction. We've also got an actual separate power supply here. So I actually, in the example video, I showed you a 9 volt battery that was connected to here. I've actually got a 12 volt power supply here. what that will simply energize the solenoids a bit more effectively. It will make the ring louder and faster to react because it will swing this clapper between them with greater force. So it will actually just make the ring a bit more intense, basically. That's what that does. But that 12 volt there is only used to power the solenoids. It doesn't actually power anything else down here. So the Arduino you would still power as normal, either through the USB connector or through the V-in socket here, or with a 5 volt supply going into this circuit here. So that is how we are supplying the power to the bells. And then the only other component we've got left is this cool button here. So this is just a completely regular switch like you would have used in many other sorts of projects, and it is going to pin 6 and also to ground. And just like the mechanical switches in our telephone earlier, we will use an input pull-up, so the pull-up resistor in the Arduino, that will make this signal read high when the button is not being pressed. And when it is pressed, it will connect these wires together. This will pull the yellow wire down to ground, and that will read a low signal. And that is it. So now that we've wired the Arduino to each of the individual components inside the phone, we need to consider how we actually want them to behave. Now, making and receiving phone calls is probably something you've done so often you may not have ever stopped to consider the process or the steps involved. But actually it's a really good idea for any kind of process or user experience that you're trying to create to try to draw and map out the complete process. So that's what we're going to do here. And I have drawn a flow diagram that looks like this. So this is what's called a state machine, or a finite state machine. And the square boxes represent all of the different states that the telephone can be in. The arrows that join the boxes together, well, those are the transitions between states. So they're the events that can happen that cause the telephone to change into a different state. So at the moment, the telephone is idle. And there are two possible event triggers that can cause it to transition to another state. The first of which is if I simply lift the handset off. Now when I do that, we've transitioned into the dial tone state. So we can hear the dial tone and the ring mechanism is now ready to receive input. If I replace the handset again like that, we have transitioned back to the idle state again and we're at the top of the flow. So if I lift the handset, we're now back into the dialing procedure again, and I can begin to dial a number. Now we kind of transition back to this state over and over in the dialing state until either I replace the handset again or a valid or an invalid number is detected. So if I actually dial a valid number this time, we have attempted to connect the line, but when we've got there, the other user was busy. So now I've got to another state, that was the engaged state, and the only thing I can do is to return to the top of the flow again, is to replace the handset. And now I can try again, and I can follow through the main line, or alternatively, I could have the other action that would cause us to transition out of the idle state. That's an incoming call. So again, I'll press the button, and now we jump down here. So the phone is ringing, I'll pick it up, and when I pick up the handset here, we have now gone to the connected state again. Finally, when the call is hung up, either I hang the call up or the person on the other end of the line hangs the call up, we transition back once more to the idle state at the top. So this is, I've kind of used state machines in other puzzles that I've done in the past, and generally escape room puzzles have a limited number of states. They are either active, maybe they're solved, maybe they're idle because they've not been active yet. This is probably the most advanced state machine that I've actually done an escape room prop, but I think it's really good to lay out those ideas, and it's actually going to make it much easier to understand the code in the following section. And here is that code. So I've written this to run on an Arduino Nano, but this should work on any model of Arduino, or indeed an ESP8266 or ESP32 as well. So we'll start at the top of the code. and so this is where we include any external libraries. And the first one we're making use of is this one called bounce. Now, bouncing in this context is referring to when you have a mechanical button or switch that is open and closed and the metal contacts come together. They can quite physically bounce apart and together again a few times, which generates a kind of a bit of noise in the signal. Now, you'll get this with any kind of button or switch, but it's particularly important in this project because remember that we are counting the number of times that number switch opens and closes as a way of detecting what digit was dialed. So it's really important that we don't generate false kind of positives that sounded like a switch being open and closed, whereas in fact it was this bouncing effect that happens. And you would have noticed this if you followed my earlier project. I know some people had problems with the receiver handset detected being lifted and then replaced and then lifted again very quickly. So this is a software debouncing library. You can use it, like I say, for any kind of switches, and it's just going to ensure that we kind of get a clean signal every time one of those switches is opened or closed, and that we don't accidentally record that noisy few milliseconds where it bounces open and closed a few times. So you can use this in any library where you've got mechanical switches, but it's particularly important here. I'm using software serial. This is because the interface from the Arduino to the DF player uses a serial interface, so we'll use the software serial library to set that up. And then this library here is the one that has the specific functionality about playing the audio files on the DF player itself. These libraries here are both saved in the source subfolder of this project, so they are referenced using these double quotes here. The software serial library, well, that actually comes with the Arduino IDE, so it has these angled brackets instead because it looks for that in the Arduino libraries folder. Then we get onto the constants. So this is the section of values that are going to remain fixed throughout the duration of the project. And the first section, all of these bits up here, these are just defining the pins that we have the different components plugged into. So if you're following the wiring diagram exactly as I had it set up, then we're using A0 to go to the hook pin of the phone, A2 to go to the dial pin, A1 to go to the number pin, and then we're using digital pins 2 and 3. They're going to the motor driver, the L298 motor driver, which is going to make the solenoid ring the bells. And then we have pins 4 and 5. That's what's going to and from the DF player. So 4 is the transmit from the Arduino to the DF player, and 5 is the transmit back from the DF player to the Arduino. And then we've got this pin 6 here. This is connected to the button that we press when we make the phone ring with an incoming call. If you wanted to have multiple buttons set up that triggered different incoming audio, you could define more pins here if you want as well. And then here we've got at the bottom, this is a different constant, so this is the maximum number of digits allowed in a phone number. So what happens is when the player is dialing a number, if the number gets recognized as one of the ones that's defined a little bit later on in the code, it will be connected automatically. But if they carry on dialing and they get to this number of digits and whatever they've dialed hasn't been recognized as a valid phone number, that's when they'll get the number unobtainable tone in their handset, and they'll have to hang up and start dialing again. Okay, so then we go on to the globals. So these are values which are shared throughout the duration of the project throughout different functions. So what we're going to do is we'll define a character array that is the phone number dialed. Now you might be wondering, well, why am I using a character array to dial a phone number? Surely a phone number should be maybe an integer or a long integer or something like that. But actually, if you think about the way that we think of phone numbers, they often have leading zeros at the beginning of them. And some phone numbers you might want to have an extension that you dial using a hash or a star symbol as well. So actually, even though we call them phone numbers, they're really strings of digits. So that's why I'm using a character array. It needs to be long enough to hold whatever the maximum number of digits we defined above was, and then one more character at the end, because that's going to have the string terminating character appended to the end of it, just to let us know that we've got to the end of the number. This current digit here, so this keeps track of whatever the digit that we are currently dialing on the dial mechanism is, and this keeps track of how many pulses we've recorded so far. So these are both used in order to actually determine the number that the player is dialing. And here is where we define all those different states which we were just talking about in the state machine. So like I say, we've actually got 9 states here, and we'll start in the idle state because that's the one where the phone is not ringing, the handset has been replaced, so that's our initial state is idle, and then we'll move through these other states depending on various events that might trigger a state transition later. So having included the bounce library up the top here, these here are the bounce objects which we're going to attach to each of the mechanical switches which we want to use that bounce library to make sure that we get a nice clean signal from. So we'll create bounce objects for each of them, and we'll attach them to the relevant pins in the setup function in a moment. We also initialize the software serial interface on the specified pins above, and we'll create an instance of the DF player as well. Again, we'll attach that to that software serial in the setup function in a moment. This keeps track of the last time the bells were rung. That's just so that we can get that the correct pattern of rings. So here in the UK at least, the pattern is kind of ring, ring, and then a 0.4 second gap, and then ring, ring again. So you get a pair of rings 200 milliseconds apart, and then a 400 millisecond gap, and then a ring again. So we'll use this counter here just to get that that pattern right, that cadence of bells. You can change that if you want later on, if you want to have a different kind of ring pattern. And finally, we'll keep track of which audio file we're going to play from the SD card when the phone is connected. So this works both for incoming and outgoing calls. We'll just update this value here, and this is a simple integer number which is going to be the index of the MP3 or WAV file on the SD card. So if it's an incoming call that's answered, this will give us the index number of the audio file to play, and if it is an outgoing call, what we'll do is we'll change this number corresponding to the phone number that was dialed, and then when the call is connected, that will give us the audio file to play. So that's both for incoming and outgoing calls. And now we get to setup. So setup is run when the code is first started, and we run through this series of functions here. So we'll begin the serial connection. So this is not the software serial connection to the DF player. This is the serial connection that's going to go using the USB cable that's attached to the Arduino, and that's what we're going to use for outputting debug information as well. And the first debug information we'll put out is going to be the name of this file, so Rotary Pulse Telephone I've called it, and also when it was last compiled. So this is just a kind of a sort of a best practice feature, I suppose. I've used it in my recent projects. I probably should use it in all my projects. It just means that if you find an Arduino lying around, let's say, and you plug it into a USB connection to your PC and you load the Arduino serial monitor, what you'll do is you'll get dumped out whatever the name of the file, the sketch that is running on that Arduino, and also what version it was, so when it was most recently loaded. And when you get to have lots of different prop controllers that are all sort of running on different Arduinos, that's actually a really useful feature to have, just to keep track of what code is running on what hardware. So that's the only reason for that. And then we declare all of the input pins. So up here in the constant section, we defined what pins we were going to use. Now we actually need to initialize those pins to the correct state. So for all of the buttons or switches that are connected to the phone, these all follow the same process basically. What we're going to do is we first of all set the mode of the pin to be an input pull-up. And so input pull-up, again, what that means is that on the Arduino board itself, there are little resistors that are going to connect to that pin, and they are going to connect through a resistor to a high voltage, which is going to be plus 5 volts on an Arduino. If you're using an ESP32, that'll be plus 3.3 volts. So when nothing else is connected to this pin, by default it goes through a resistor to a high voltage, and so it's going to read high by default. If it is then connected, in this case, to the hook pin, the dial pin, the number pin, or that button which we're pressing to make an incoming call, it connects through that to ground and the switch is pressed. What that means is that the circuit is made from that pin through to ground, and it will read a low signal instead. So that's why we're using the input pull-up here. And once we've defined the pin to be in the right state, we will also then attach, this is the bounce object that we created up here. So all these instances of the bounce class we used up here, we're going to attach that to the corresponding pin, and we're going to set the interval. So this is in milliseconds, effectively how smooth we want to receive that debouncing effect. So in this case, we need to have received a constant low or high reading for at least 5 milliseconds before we definitely say yes, the switch has stopped bouncing around now, we're getting a constant signal, let's update it. So this is slightly different syntax than you might have seen me use before. If you're just using a standard button, normally you'd just use this. It's got this extra bit at the bottom. That's because that's what we're using to attach the debouncing object. Okay, now the ringer pins, these are what's going to the motor driver to drive that 12 volt signal to the bells. So they are going to be output pins, and we'll initialize them as low. So to start with, at least, we don't want to be powering those solenoids at all, so we'll just have a low signal. Then we'll initialize the output to the DF player. So first of all, we create the software serial interface here, and we'll just check that that was actually successfully initialized. If it was, we'll dump a message, and if not, we'll wait a little bit, give it 10 tries to initialize before saying that it's failed. And so this is something I found, depending on the particular batch of DF player modules that you get, you'll find that some of them kind of come online immediately. Some of them you have to kind of power them for a few sort of seconds before they're able to respond to an input from the Arduino. So that's kind of why this section is here, because depending on exactly what manufacturer you had, you might find that you need to kind of install a little bit of a delay before it comes online. So that's the reason for adding that bit there. Once it's there, we'll set the volume level that we want. I found I actually need only a very low volume here because the speaker earpiece that I've got in my phone is actually very loud, and I only need to use a low value, so I'm using a value of 6 here. And finally, we'll just ensure that that number array, which we defined up here, will actually make sure that there's nothing in there at the moment, that we haven't got any sort of stray bits of memory hanging around there. So we'll set that to be all 0 to start with. And that's the end of the setup. So now we go on to the loop function, and this is basically the body of all of the program that handles all of that state transition, what happens to the phone in each of the states, what is allowed to move it into other states and things like that. So this is the real meaty bit of the code, but hopefully this is not going to be too hard to follow, having been through that flowchart already. Because as much as possible I've tried to make this mirror exactly how that flowchart worked. So on every iteration of the loop, the first thing we do is we read the current state of all of the switches. Now, normally in an Arduino, if you want to read the input on a pin, you'd use a function called digital read. But because we are using these extra little bounce objects here, we don't want to take the raw digital reading. What we're going to do instead is we're going to update our bounce objects, and then we're going to look at the output from that and let them tell us, has the signal risen, or is it high or low, or has it risen or fallen. So to do that, the first thing we need to do is actually update all those readings, and then we start stepping through our logic. Now the first thing is to look whether the hook switch has risen. Now that's what happens when the receiver is replaced back onto the handset, because what that does is that opens the switch, which means that the pull-up resistor kicks into action. It pulls the signal on that pin up to high. So if the hook switch has risen, we don't really care what state we were in previously. As soon as that happens, as soon as the handset is replaced, what we want to do is to set the phone back to idle, because it doesn't matter whether we're in the middle of making a call or whether we were on a call or whether it's engaged or whatever. We set the state back to idle. We stop any audio that might have been playing through the earpiece speaker, and we also reset any stored details we might have had of the number that we were dialing. So we set the number to 0, and we also reset any count of pulses we might have been in the middle of, things like that. So this section here is at the top. This is outside of the rest of the conditions, because this is kind of like an immediate override basically. I could have put that into the switch statement at the bottom, but I would basically have to repeat this section of code in every state. So it's more efficient just to write it at the top here. Now the following section though, what this does is this has different sections of code that get executed depending on the state that the telephone is in at the moment. So that's what this switch and case bit means. This is a bit like a series of if statements, if you're familiar with them. It's just a slightly different way of laying it out really. So we're going to switch our behaviour based on the current state of the telephone. Okay. Now in the case that the state of the telephone is currently idle, this is the section of code that's going to get executed. And we had two possible actions we were listening to in that state. The first one was that the receiver is going to be lifted up. Now, if you remember from the code up here, we were listening to the hook switch rising, meaning that the handset had been replaced. So the opposite of that must mean that the hook switch falling means that the receiver has been lifted. And when that happens, what do we want to happen? Well, we want to play the dial tone, and we want to update the state to say that we are now in the dial tone state. Okay. The other thing that can happen if the phone is currently in the idle state is that we might receive an incoming call. So in that case, we listen to the incoming call switch falling, and when we do that, we'll change the state of the phone to ringing, and we'll play, we won't play the audio file yet, but what we'll do is we'll set the index of the audio file that we want to play if that call is answered. So this is kind of priming the audio file to get it ready so that when the call is answered, this will be what is played. And again, so you could duplicate this section here with many different incoming calls, switches which played many different audio files. Or perhaps you could have a random function here that arbitrarily chose one of a number of different audio files to play. Or perhaps instead, when we're in the idle state, if you're using an ESP8266 or an ESP32 that have inbuilt Wi-Fi functionality, maybe you want to trigger an incoming call over Wi-Fi. So if a message is received over MQTT, for example, from a Node-RED server or from software like M3 or ERM, something like that, this is the section here where you would add in those additional conditions to say this is other things that can trigger an incoming call. Okay, so that's all the things that can happen when the phone is idle. What happens if the phone is currently in the dial tone state? Well, in that case, there's really only one thing we need to listen for, and that is that the player has started dialing a number. So what happens when the dial mechanism is rotated and then returns happen? Well, that is the dial switch falling, because again that means it's been connected to ground. That means that the rotary mechanism is rotating, and we are then in the dialing state. So we'll just log a little message to say we're in the dialing state, and we will stop the dial tone from playing because, and I had to check this on my own phone at home actually, that is what happens. The dial tone only plays in the earpiece when you lift up the handset until you start dialing. At that point it stops. So that's what's going on there. Alright, so we've moved on. We're now in the dialing state. So this is the most complicated state, I suppose, in that it handles the most amount of interactions. So what can happen when we are dialing? Well, one thing that can happen is that the number switch might change state, particularly it might rise. Now, when the number switch rises, that means that another digit has been passed as the mechanism returns back to 0. And when that happens, we're going to increase our pulse count. Now, we don't know yet what number is being dialed. All that we know is that we've received another click on this switch here. We need to wait until the mechanism has actually returned all the way back to the resting position to know that the number has been dialed, and that's what happens here. So this bit here will keep on getting looped over and over and over. Each time the number switch clicks, we'll increase the pulse count. When the dial switch rises, well, that was the switch that changes state when the handset returns to 0. Now when that happens, we know we've got to the end of the digit being dialed. So we can take our number of pulses, and there's a slight exception of the rule here, because if it's a 0, the 0 is actually the last digit on the phone handset. It comes after the number 9. So if we get 10 pulses, that was actually the digit 0 being dialed, not the digit 10, obviously. So we'll do a little workaround there to say, okay, well, if the number of pulses were 10, what actually happens is 0. Then what we will do is we will take our pulse count, we will convert it to a character value, and we will put it in the last place in our number. So this is our array. Remember that this is the array that we defined up the top here, which is going to be a character representation of the number dialed. So what we're going to do is we're going to take the number of pulses that we received, turn it into a character, and append it to that array. And we will also increase the current digit along. So the first digit we receive will obviously become the first element in the number array. Once we've recorded that, we'll go into the second element of the number array, then the third element, and so on and so on. And then what we'll do is, okay, well, whatever the value of this is now, let's test that against all of the numbers that we want to have an effect, basically. So to do that, we use something called str&comp. So this is a comparison function that compares the certain number of digits of a string to another string. That's what this says. This is a standard C function. And so what we're going to do, first of all, let's compare whatever number has currently been dialed. Let's compare it to the string 911, and we'll just take 3 characters to make that comparison, because 911 is a 3-character string, obviously. We'll say equals 0 because that's what the comparison function does. The comparison function will return 0 if there are no differences between them. So this is a slightly complicated way of looking at it if you're not familiar, but what this basically says is there's no differences between the first 3 digits of the number dialed and 911. And that's a sort of very roundabout way of saying the player has dialed 911. And if that's the case, what are we going to do? Okay, well, let's change the state to connecting, and we'll set the audio file to 1002. So when the call is answered, this will be the audio file that relates to whatever we want the player to hear when they dial 911. Then we'll go into the next case down. So, all right, well, what about if the first 5 characters of the number that has been dialed are the same as 11111? Well, in that case, that's a different number that we want the player to get a message for. So we'll play this audio file instead. Sorry, we won't play this audio file yet. What we will simply do is we'll queue up that audio file to be played when we get to that stage. Here's another example. So we've got, what about if the first 5 characters of the number array correspond to 1, 2, 3, 4, 5? Well, in that case, I've done something slightly different here. I've said, okay, well, let's say that that's engaged instead. So we'll set the state to engaged, and we can, in that case, directly play the engaged tone here. So these ones here I've put as connecting, and we've put the audio file there. The engaged I'm playing straight away, and this is just to sort of show you a little bit some options about how you can set this up. In practice, I guess most of the time the way that I expect this to be used is that the numbers that players dial will always behave the same way each time, and in that case you can kind of go straight on to the state you want them to be. But the reason for adding this extra state here of connecting before playing the audio file is to give you that opportunity to dynamically change the behaviour if you want. I gave the example earlier to say, okay, well, maybe at the start of the game a phone number is busy or engaged, and then maybe later on in the game it becomes available. Or maybe the first time you dial a number you get one message, and then when you do something else in the room you get a different message later on. The way that these statements here are constructed means that you can add, let's say you could put an if statement here to say, if this other trigger has fired, then we'll set the state to connecting, otherwise set the state to engaged. Rather than playing the file straight away here, we'll simply queue up which audio file to play, but whether that file actually gets played or not could depend on a different condition being met or not. So I've kind of tried to demonstrate a little bit more of the flexibility of how you would set up those kind of scenarios, I guess. That's the point for putting this example here in. And again, we've got another example here. So we've got if the current digit being entered, so that was our counter here, if that is equal to the maximum number of digits in the phone number, if we've got all the way down here, we've tested all the phone numbers we know about, and we haven't found a match, and if we get this far, but we've dialed the maximum number of digits, then it must be an invalid number. So at that point, we can say that we're an invalid number, and we can immediately play the corresponding file, to say number unobtainable or whatever. And then finally here, well, we've dialed a number, it hasn't matched any of the known numbers, but we haven't exceeded the maximum number of digits either. So what we'll do in that case is we will just go on to the next number in the sequence to allow the player to dial the next number. There we go. So that's quite a meaty section. This is the most complex state, because this is the thing that actually deals with the majority of the handling the actions that the player can take. But hopefully you're able to follow that. And then we just move on to the final few states. So we have the connecting state here. So this is the kind of the intermediate state that gets passed through after the players have dialed a number that's been recognised, but before the phone has actually been answered. So what we do first of all is we play a sound effect of just the phone ringing, and then players have to wait for the other person to answer the phone. So in this case I've put a 4,000 millisecond delay there, 4 seconds. You could adjust that if you want. You could have that as a random value between two limits if you want, just to add a bit more interest to it. And then assuming the phone is answered, then we then play the selected audio file that was chosen up here depending on which phone number was dialed. So This sort of connecting state is just sort of an intermediate state basically that comes after dialing and before being connected. And it's just an opportunity to add, let's say, some more kind of flexible functionality there about how the call is made. And then we have these states that go with the other outcomes of dialing a number. So whether the call is engaged or invalid or connected, in terms of the state machine itself, it actually doesn't make any difference which one of those conditions we're in. We'll be playing a different sound effect because that was chosen either up here in the case of engaged or invalid numbers, or it was set in the connecting state in the case of a number that's dialed. But actually, nothing else happens in those states. The only thing that can break out of those states is replacing the handset. And remember that we were checking for that in this function here outside of the state machine anyway. So we don't need to have any code in those states at all. I'm just kind of including them for completeness, as it were. And then the final state that we have is the situation in which the phone is actually ringing due to an incoming call. So this section here, this is all dealing with that pattern I was describing of making the bells ring. So again, you can tweak the numbers here if you want to get a slightly different effect. But from everything I've read about the UK phone network, the way that this happens is that we have 0.4 of a second in which the bells ring. So for that, I want to alternate high and low signals between my two ringer pins. So that's what we do here. So I'm going to loop over 20 times, choosing between high and low values on the 0 and 1 pins. And then I'm going to do that twice over to take me to my total of 400 milliseconds. So just to sort of explain a little bit more what's going on here. So we're increasing a loop between 0 and 20. And in every iteration of that loop, if it's an even number, so this %2 here, this is what's called a modulo. So that works out the remainder when this number here is divided by this number here. So if I'm dividing I by 2 and the remainder is 0, that means it must have been an even number. So in that case, what we're going to write is we're going to write the value 0 to ringer pin 0. And if I do 1 minus that, then what I need to have is the opposite value. So in this case, it's going to be a 1, which I'm going to write to ringer pin 1. Now let's suppose that I is an odd value. Well, in that case, the remainder when I modulo 2 is going to be 1, because the remainder when you divide I by 2 of an odd number is 1. So then I write a high value here, and 1 minus a remainder of 1 is going to give me a 0 value here. So what this does is, as I increments from 0 to 20, on every time I changes, we're going to toggle between writing a high and a low, and then the next one we're going to write a low and a high. Okay, so it's a little bit complicated, but hopefully you followed that. And then we'll do it in kind of 2 batches, because what I want to do is I want to check that the call hasn't been answered in that time. So what we'll do is we will check within the inner loop here, we'll see whether the hook switch has fallen. What that means is that the handset has been picked up, remember? So this was exactly the same as what we had right at the top here to see whether the hook switch has fallen. That means that the handset's been lifted up. So if that's the case, what we want to do is we want to break out of this loop. We want to stop the bells ringing, and we'll do that by setting the outer loop counter here to 2. Because as soon as we do that, we're not going to repeat the second batch of ringing. So I hope that I hope that kind of makes sense. So this is a way of getting a ringing pattern that can be interrupted by having the handset lifted in the middle of it. That's what that does. And when the handset is lifted, what are we going to do? Well, we're going to stop the bells from ringing. We'll set the last ring time to now, which means that in 4 seconds time we can repeat that whole process again. And for as long as we stay in this ringing state, this whole section of code here is going to go ring, 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 wait for 0.2 of a second, ring, 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 ring again, and then wait for 4 seconds before doing it all again. Okay, well, what else can happen when we're in the ringing state? First of all, we do check here, but if the hook switch has fallen, that means that the call has been answered, and what we will do is we will play the audio file here, just as we did when we were going straight to an engaged tone or going straight to an invalid number tone. Now we've had a ringing tone or a connecting tone, which is when we have an outgoing call. This is an incoming call. And again, we will just play the selected audio file through the speaker. And that is the last case in our state machine which we need to account for, and that is the end of the code. So that's my version 2.0 escape room telephone prop tutorial. And I've tried to include a lot of the features which I've either seen used or used myself or that people have requested. I'm sure there are still additional features which you could conceivably add to this. One obvious thing I've not made use of at the moment is the microphone, for example. That's because the Arduino microprocessor is not really capable of doing any useful audio processing on the signal. But if you had a more advanced piece of hardware, it is possible, for example, you could do some sort of primitive voice recognition. So that's something you could add in the future. I've tried to make the code as modular and as extendable as possible so that not only can you add new phone numbers that you want to see recognised, but if you want to do other hardware outputs be controlled by the telephone, those are easy to add as well. And throughout this, I've also tried to explain the way that I approached designing it with this handset in mind, so that if you are somewhere else in the world, if you're using a different style of handset, you can hopefully still adapt all these steps to make it work with whatever you've got to hand. As always, if you've got any comments or questions, please do let me know below. I will put the wiring diagram and the code downloads and the links to where I got all these bits and bobs on my Patreon page. I am very lucky to be supported by some amazing patrons who make it possible for me to create these videos every month. So thank you very much to all of you, and do head over to my Patreon if you'd like to see more escape room tech projects like this in the future, or any of my previous projects I've got downloads for over there as well. In the meantime, I will simply say thank you all very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.